And we had an ambitious vision. We wanted to make it so that any application could easily add in real-time communication with audio, video, or their own application data. And we wanted to build this on top of open protocols and open source so that others could help us build a great ecosystem and contribute back their own improvements. We were also super focused on performance. We wanted to make sure that apps could deliver state-of-the-art quality to be competitive with anything else that is out there, routing media peer-to-peer when possible. And we also wanted to make sure we could provide end-to-end encryption so that developers can make sure their users' communications were safe no matter where they were in the world. So we presented these ideas, and we got a typical Google response. Sounds great. When can we have it?
It's like the moment when you think, what was I thinking? Crazy plan, but anyway.
Anyway, I mean, it's a good question, but in hindsight, it worked out pretty well. We went off and built this platform for real-time communications, and it's called WebRTC. At the same time, while we're building this, though, we saw this incredible shift to mobile, where communication takes even a higher importance. Mobile users spend more time in communication apps than any other type of app. In fact, 6 out of the top 10 most used mobile apps are communications apps. So we worked hard to take the APIs we built for WebRTC and the web and bring them to Android as well as iOS and provide platform native bindings so people writing applications can easily use this code on any platform they wanted. You can now write apps, communication apps in the same way across web, Android, and iOS.
So, yeah, look, we'll just change the name, yeah? So, this is good, yeah? It's nice, it's catchy.
Yeah, I'm not quite sure that's an improvement.
Oh, I love it.
Names aside, though, WebRTC is seeing terrific adoption. There's over 1.5 billion browsers out there that support WebRTC, between Chrome, Firefox, Opera, and now Microsoft's new Edge browser. And this is powering major apps like our own Google Hangouts. And on mobile, there's been terrific momentum as well, where WebRTC is powering these top applications I talked about before, the most used applications on mobile. WebRTC is powering many of them. There's over 3 billion downloads of WebRTC-powered applications to date.
So, yeah, I mean, developers are adopting WebRTC, across the web, Android, and iOS. And, we're going to show you now really, kind of just how to get started on all those platforms. One thing you'll find, if you're a web developer like me, happily, the APIs on the native platforms, really parallel those on the web. So, yeah, let's get started with that. So, obviously, for a real-time communications app, the first thing we're going to be able to do is get audio from the microphone and video from the camera and get that into our app. Now, on the web, as some of you may have encountered, we use the get user media method, and that gives us a media stream object. And here you can see it in action. So in the callback there, we've got a media stream, and then we can do something with that local stream once it's received.
So that media stream contains audio and video tracks, which represent the media flows from the camera and microphone. And on Android, we have the same concept, media streams that contain tracks, but you sort of put them together yourself. And this allows more control. On Android, you create this video capture object first. And this allows you to specify exactly what device you want, whether it's the front camera, whether it's the back camera, and then you manually create an empty media stream, just like this. And then you take that capturer, wrap it in a track, and then push it into the media stream. So it's very similar to what Get User Media does for you in the web, just here, more assembly is required. On iOS, the concepts are very, very similar. Instead of the video capture object, it's just called RTC Video Capturer. And here with the delightful Objective-C syntax, we create the capture device, specifying what front or back camera we want, make our own empty media stream, and then make a track that wraps that capturer, and then we add it to the media stream. So now once we actually have a media stream, now it's time to do something interesting with it.
So we've got our media stream, and then we need to be able to transmit this to other users, yeah? Like from one peer to another. Now, on the web, we have for this the RTC peer connection API, and you know, this is the core of WebRTC. RTC peer connection does a lot. You know, signal processing, peer-to-peer communication, bandwidth management, security, codec handling. You know, you get the picture. So let's look at that in action. So we've instantiated the peer connection object, and then on AdStream enables your application to be able to handle an incoming video stream, a media stream. And AdStream, the method on peer connection there, enables you to send a stream to a remote user. Now, peer connection also enables your app to get information about how and where to send audio and video. And once that information is obtained, you can share that with other peers via any mechanism you choose. You know, that process is called signaling, and actually Justin's going to talk a little bit more about that later.
Right, so Sam mentioned that we need to make sure that we can plug our media stream that we had into a peer connection so it can be transmitted to the other side, and also register for incoming streams so that we can render them. And it's a very similar process on Android. We create the peer connection, we create an observer object, pass an observer object to receive those callbacks, like when a new stream is received from the other side, and that's a very common pattern on Android. We plug in the stream that we got from our own camera, the local stream here, and then we kick off the signaling process with this method we call create offer. And this gives us a callback on our delegate, who gives us the information, this how and where to send media, that we can then send to the other side in order to get the actual handshaking and the actual media transmission started. On iOS, it's very similar. Again, we have the peer connection object. We create it, we pass in a platform-specific way to get callbacks, this delegate object. We add the stream that we're going to send to the remote side. And then when we get, we call this create offer method to kick off the signaling process, and we pass in a delegate saying, hey, go create this information we need to send to the remote side, and when we're ready, let's go send it off to the remote peer.
So once we've got the media stream, we then need to be able to render it somehow. And on the web, this is really straightforward. We can stream incoming media streams directly to a video element using the create object URL method. As simple as that.
And on Android, we have a little bit more control again, and we have an OpenGL-based video renderer. And what this lets us do is we get hardware-accelerated, GPU-backed video rendering. So it's like very high performance, doesn't use a lot of CPU, and it's super smooth. And the way we hook this up is that when we get this callback from our delegate, saying that the remote side has sent us a stream, we get the video track out of that stream, and then we pass that into the video renderer object, and it does all the heavy lifting to actually play out this video using the OpenGL hardware acceleration. We just add the renderer to the track, and it off it goes. On iOS, we have the same sort of thing. We can take advantage of the GPU once again, get this really high performance rendering. The syntax is just a little bit different. We get the Objective-C, this callback in our Objective-C syntax on our delegate object. We get the track out of the stream, and then we just add it as a renderer to we add the GL renderer as a renderer for our track. And that's all it takes to render the video.
So, we've just kind of scratched the surface here. I would really recommend, there's two great guides just been published, one each for iOS and Android, and you can get access to those from the URL below, or if you look at the slides, they're linked to from the slides as well. Great introductions to native WebRTC development. So, we had, these very powerful APIs, and of course, the first thing we wanted to do was to build, a really good demo app. We wanted to enable people on iOS and Android and the web to be able to get a really great video and audio experience. So we built an app, and we called it WebRTC, and Justin's going to tell us a bit about that now.
So when we built this, we didn't want to just build a bare bones ordinary sample app. We really wanted to build something that could show off what WebRTC is capable of. The highest quality audio video, super fast call setup, and strong encryption. We wanted to make this open source so others could study this and use this code to create their own applications. And again, we wanted to do this across web, Android, and iOS. So,
yeah. So, anyway, I mean, enough with the talking. We'd just like to show it off now. So, I'm going to open up WebRTC on the Chromebook here, and you can see we're getting video from the Chromebook camera. And Justin's going to connect to that via the Nexus 6. Oh, it's already happened. There we go.
So you can see here that we're streaming video right off this thing using the conference Wi-Fi. I'm getting the nice 720p HD image coming off the front camera, and let me show you from the back camera that really helps demonstrate what this is able to do. I mean, here we are using the power of the hardware codec that's built right into the Nexus 6. Android supports this to the media codec API. We wire this up in the WebRTC stack, and basically from this device I'm able to send this beautiful 720p HD stream that's fully encrypted here to this display. And so it's not just the stream that we're able to send that's really great. If you take a look actually here at the video we're receiving on the device, we're getting an awesome image coming off the Chromebook as well.
Yeah, that's fantastic.
And so this is what we've been talking about, the ability to build these fast, secure, beautiful communications experiences into apps across Android, web, and iOS. This is what WebRTC is able to do.
Yeah, that's fantastic. A little geek trick there, by the way. If you're running WebRTC, you can press I, the letter I, and you'll see you get a whole bunch of interesting stats up here. You can see we've got 720p, and yeah, we've got direct connection actually there, and a whole host of other interesting other stuff going on there. So yeah, for the WebRTC geeks out there, you can try this app out. It's at appr.tc. And the code for WebRTC is available. The web app is at GitHub, and the native versions you can have a look at from webrtc.org. And yeah, it's all open source. You can download the code from there. So one thing, I just wanted to say about the app was that the the interface you'll see is pretty minimal. We really focused on performance. Now, I'd love, Justin's going to tell us a little bit more about how we achieved good performance with the app.
I think so. So we really wanted to let the sort of UI just get out of the way and let the performance speak for itself. And let the video, what you actually want to see, that be the main focus of the app. But there's a lot of stuff that goes on behind the scenes to make that app snappy, to make everything work really well. And so we talked a little bit before about signaling. In order to set up a call, WebRTC apps need to first exchange connectivity and media metadata, and they do this through the cloud. They send this information through the cloud that gives them the information that can then be used to set up that direct connection between the peers. And so this media metadata is the how and where to send media. Now, it's pretty easy to send a message to the cloud, but sending messages from the cloud down to devices is a bit trickier. And so for WebRTC, we use WebSockets for this cloud-to-client communication. And we stood up our own WebSocket servers on Google Compute Engine. And when we did this, we found that WebSockets are really, really fast. The fastest thing we found, and we found that we could actually transmit these signaling messages end-to-end in under 100 milliseconds. So we also looked at making our signaling smarter to figure out where we could do work early so that we wouldn't be able to optimize that call setup process. And so for WebRTC, while we're waiting for that second user to join into the call, we cache all the first user's media metadata information at the server. So as soon as that second user joins, all the information can be sent out instantly and the call gets set up. So one other thing that's important to talk about is WebRTC tries to set up peer-to-peer connections, but we sometimes encounter networks where that's not possible, and we need to use relay servers, also called turn servers. And it turns out this is actually more common on mobile networks, 3G, 4G, LTE, just due to the way the operators set up their networks, which makes it even more important to make sure that we have relay servers set up in a way that doesn't cause media to go on a very lengthy round trip. So to make sure that whenever we had to use a relay, it didn't slow things down, we use something called Tailbone. And Tailbone is an open source App Engine module that will dynamically spin up turn server instances and multiple Google Compute Engine zones so that we can basically have servers close to every single user and handle any level of demand dynamically. And so Tailbone will spin up basically when it sees the instance of the turn server is loaded, new versions of the turn servers, And we also can run this in every single Google Compute Engine zone. So around the world, every user has a turn server within a few, 100 milliseconds or so. The actual turn server that we use is an open source turn server called CoTurn. And we run this on GCE, where Tailbone is creating these VM instances that have self-contained packages of CoTurn already. Now, previously we talked about some big numbers for WebRTC, but now we'd like to end on a small number. So 500 milliseconds. When you take all the improvements I just talked about and put them together, this is a typical call setup delay that we're able to achieve with WebRTC. From clicking the join button to live video chat in half a second.
That's great.
So we say performance is a big part of user experience, and WebRTC lets you create apps that do high performance.
Yeah, that's great. So, like we say, all the code for AppRTC is available. You can get to all the information from g.co/WebRTC and a stack of other, useful samples and so on available off there as well. Getting started with WebRTC. And please, we really appreciate your feedback. Go to the website or use the Google I/O app. And yeah,
thanks for coming. Thanks for listening. If you have any questions, we'd love to talk to you after the session. Catch us here, right outside, or you can come visit us at the Android device wall. Around the corner.
Yeah, if you haven't seen that, it is fantastic. The device wall just around the side there. Go and check out your website. It's on like 50 different devices. So yeah, thanks so much for listening. We'll see you around.
Thank you.